to everyone. So, in today's lecture of this thermochemical surface treatments, we will discuss about the kinetics of the growth of nitrided layers when we are doing nitriding with the conditions such that it does not allow formation of any other iron nitrogen phases. That means, the matrix remains ferritic. So, only the alloying elements which are present in the ferritic matrix will interact with the inwardly diffusing nitrogen, and that is what leads to the development of the nitrided layer. So, in the previous lecture we have seen the layer type growth of nitrided region. I call it as a layer type growth because we do not have any defined compound which is growing like iron nitrides rather than layer growth. So, we have in that situation, for example, for iron chromium, iron vanadium, and we have not discussed, but it is known that iron titanium will also behave more or less similarly. So, you see that if you look at as a function of depth, for example, the nitrogen content, this is the nitrogen content as a function of depth, see something like this. So, where you have a unreacted core and you have a nitriding front growing up. Now, this has a certain, it has its own kinetics of growth, this layer. So, we are interested in now to understand how to understand the growth rate of these layers, for example, at given conditions of as a function of time for a given temperature and nitriding potential, or if we are changing the temperature by keeping the nitriding potential and the time constant, how the temperature actually changes the growth of these layers. We have seen that these parameters does influence the growth rate in the previous lecture. So, now to define some quantities, let us say that this level is the concentration of nitrogen as a layer. For example, I use the term layer. So, this level I would define it as a CN layer. Okay. This is actually the total nitrogen level, right. This is the total nitrogen level that has actually the different contributions to this total level as a dissolved nitrogen which we have discussed, and the nitrogen which is bonded with the nitrides. So, in this case, for example, if we take the chromium, for example, the nitride bonded with chromium nitride. So, and we have discussed also N excess. Okay. I will not go into the details of that, but we can say that all this together we have a CN layer. And if you look at what is this level of this CN equilibrium alpha iron, okay, this amount is a maximum 0.4 atomic percent. Okay. That means, if we see in this total nitrogen profile, in this total nitrogen, if we try to look at what are the way this will be there, that will be rather small. Okay. So, you will have maybe something like that. Okay. And this is the only nitrogen which is participating in the diffusion process. Okay. Because this nitrogen which is bonded with the nitrides is actually the sort of a frozen nitrogen. So, that nitrogen will not participate in the diffusional process. Now, to understand the kinetics of the nitriding process, you know that several reaction rate steps needs to be considered. For example, this is the sample and you have here the gas atmosphere, and now the rate at which the molecules of the gas atmosphere that come to the surface of the sample. Okay. This is a rate of supply of species to surface. this can be sort of one rate, and then at this surface you will have the another rate controlling mechanism could be rate at which species react with surface. And then we can see that another thing, once the species are here, then you can have that within the sample you can have another thing, this is the rate at which nitrogen diffuses into sample. So, now it is important to know the rates of these steps, and then we can figure out actually either one or the combination of the two or more of these rates could be rate determining in the overall growth of the nitrided region. So, for example, this one rate of supply of species to surface we can neglect if we are sufficiently making the flow of gas in the or a mixing of the gas in the furnace atmosphere. So, this species coming to the surface can be assumed to be not a rate determining step. So, this can be we can neglect. Now, the rate at which species react with the surface, right, this cannot be neglected, or because this in particular with the nitriding, the rate at which the ammonia dissociates at the surface of iron, having it is a finite rate. Okay. So, that is what is actually allowing the practicability of nitriding, because if this nitriding rate is very fast, then we will not be able to maintain the defined level of ammonia hydrogen gas mixture in the furnace, right. So, this gas is actually NH3 plus H2 in the case of nitriding. Now, if the rate at which ammonia is dissociating is very faster as compared to the rate at which nitrogen can diffuse inwardly, then you will start to produce the hydrogen and nitrogen into the gas atmosphere, but that is not the case. So, this has its own finite rate, and then you have a certain rate at which the things are diffusing into the sample. Now, in order to understand this diffusional kinetics, let us just recapitulate the diffusion equations, the fixed diffusion equations. For example, if you have a concentration having a certain profile like that, and now for example, if you are looking at this is the diffusion direction, okay, and this is the depth along which diffusion is happening. And now at this if you look at the specimen cross section, what would be the flux of, for example, in this case the nitrogen leaving this cross section, that would be proportional to the gradient in the composition, okay, that is this slope at that depth, okay. That is what actually the flux of species, for example nitrogen, is proportional to the gradient in the nitrogen concentration as a function of depth at that depth, right, at this condition. That is what gives us this, and then this proportionality constant is the diffusion coefficient of nitrogen in the whatever the matrix we are considering, that would be in the particular case of nitriding we are considering would be the diffusion coefficient of nitrogen. Now, if we assume that this concentration gradient is constant at different depths, that means you have a linear profile, then actually the flux of nitrogen leaving at any section would be the same, okay. The flux of nitrogen Jn would be the same, that means you will not have any change in the level of these nitrogens as a function of time. That is why this is called steady state diffusion equation. This is the this equation is called steady state diffusion, because this will not be able to give you the rise in the composition as a function of time at the that is what happens usually in the real situations. So, that means if you have a concentration profile at time t, this is the concentration of nitrogen as a function of depth. Now, at some other time t plus delta t, you would expect it to be coming out like that. So, this is at let us say t plus delta t, and now if you take any constant depth, now this has gone up from this level to this level in a given time, the delta t. Now, if we want to know this, what is actually making this level to change, that should be only possible for this accumulation if the flux entering this region, like say that this is a finite region, entering from this section should be more than the flux of nitrogen leaving from this section. So, that is only possible from this equation if your concentration gradient is different at these 2 points. That is the case here. If you see the way the diffusion profile comes, here the gradient is more than here. So, the flux entering at this section, okay, let us say that this is x 1, would be more than the flux leaving the section at x 2, that is what lead to the accumulation. So, that is where you can get the expression for the Fick's second equation, that is the way the concentration of nitrogen changing as a function of time at a given that depth would be given as this accumulation is because of change in the flux from the steady state diffusion equation within this delta x range, okay, that is the dou n by dou x. So, here you will see that there is a minus sign which I have not placed before, because the diffusion happens against the along the concentration gradient, and this gradient is negative if you see as a function of depth. So, whereas the net flux goes in the opposite direction, that is where you will see the negative sign. Now, if you use the J n as we see it here, then this is what we end up with the Fick's second equation. Now, if you treat the diffusivity of nitrogen is independent of composition, then this is the how one can write the Fick's second diffusion equation. Now, in order to precisely model the nitriding process, one need to solve this diffusion second Fick's diffusion equation using appropriate initial and boundary conditions. That is actually not which I will be covering, but I will be only covering the simplistic model which has been always used in understanding the nitriding kinetics in this kind of systems, okay, by assuming a steady state diffusion of nitrogen into the sample, okay, that is what I would explain now. So, in that situation, because we know that the amount of dissolved nitrogen is very small as compared to the total nitrogen. So, we can assume a linear concentration depth profile. Okay. So, the first in this simplistic model, there are certain assumptions which are made, that is what led to the simplicity of this model. So, the first thing is there is a these are the assumptions of this model which we will be considering. There is a linear concentration versus depth for the dissolved nitrogen, and this is this depth will be present, this gradient will be present within the diffusion zone, and the second assumption would be the surface reaches equilibrium level of nitrogen instantaneously. That means, at t equal to 0, the concentration of nitrogen at the surface will be concentration of nitrogen expected for the equilibrium. Okay. We are talking about the dissolved nitrogen. So, this means your concentration profile will be like, if you look at actually the assumption which we are making is, if this is the concentration of nitrogen as a function of depth, what we say is that this concentration is already reaches at time t equal to 0 as Cn as equilibrium. Okay. This is Cn equilibrium, and you have a linear profile into the sample. Okay. As a function of depth, if we use the parameter L, so you may be having different depths, right, but which is with respect to the same level, and you have a linear profile. Okay. So, that is what is the assumption, and now using these two assumptions we can actually try to build the model. For example, you have we have a nitrated region growing. Let us say that at some stage this is the nitrated region with this level of nitrogen as the total level, and you have a dissolved nitrogen profile. For example, it is, I will use a different color. So, you have a dissolved nitrogen profile which is going linearly like this, with this is the Cn of layer, that is the total nitrogen level, and this is the Cn equilibrium, that is the equilibrium level of dissolved nitrogen in the alpha iron, and you have a linear profile. For example, if you see that for a time step of dt, okay, if I take a time step of dt, what would be the amount of nitrogen that can be crossing this level. Suppose if we use the depth is represented as a parameter L, okay, that is increasing. Here you have a 0 for both x and y axis. What is the amount of nitrogen that can be supplied, or the flux of nitrogen for unit time at this depth L, for example, okay, some depth L, that would be that Cn would be, that one can get it from the first equation of the fixed first equation, that will be diffusivity of nitrogen times the gradient in composition. In this case the gradient would be, this is Cn equilibrium divided by L, right. This is the slope of this concentration linear profile, that is what actually we can Cn equilibrium by L, and that is for a, this is for the concentration per unit area per unit time for a time step of dt. This is the level of concentration that will come at this depth which we are choosing. At this depth, this is the amount of nitrogen, okay, that comes at a time dt. Now, next is, if we assume that all this nitrogen which has come at the time step dt, okay, will be arranged as a layer. Okay. This entire amount will be put as a thin layer, however thin it is, that depends on this amount, to lead to a increased in the depth by dl. Okay. So, that means we have a nitrogen which is diffusing here, and then you get some flux at the nitrated region end, and this entire nitrogen will be now put into a layer. So, what is the mechanism by which it will happen, that we will not bother. So, that as it is, that is not rate determining. So, that will be going into a layer. So, now the level of that would be the level of this entire nitrogen in this, the hatched area, that is the dl thickness nitrated layer, will be Cn layer multiplied by dl, right. This amount will be equivalent to Cn layer times dl, right. So, now if we integrate this expression from the thickness from 0 to L and the time from 0 to t, and then what we end up with the dn Cn equilibrium divided by Cn layer into dt equal to L into dl. If we integrate it from 0 to L and from 0 to t, we end up with, I will be writing here. So, we end up with the dn Cn equilibrium divided by Cn layer into 2, because the integration of L dl would be L square by 2, and if you take the 2 onto the left side, into t equal to L square. So, now you see the relation between the thickness of the nitrided region with respect to the time, and the dependence of the, we know that it depends on kinetics, would depend on the temperature and the nitriding potential. The temperature effect is included in these two quantities. The Cn equilibrium has its own temperature, it depends on the temperature and the nitriding potential that we have discussed previously, and similarly the diffusivity of nitrogen, it also has its own dependence on temperature, that is dN has its own exponential dependence with a certain activation energy. And knowing these, now actually the independently we have the measurement of diffusivity of nitrogen in ferrite, as well as independently the measurements on how the equilibrium level of dissolved nitrogen changes with temperature and nitriding potential for a pure iron. So, knowing this, now from the, if the whatever the assumptions are made in this model are the really justifiable, then when we do the kinetic analysis, we should be able to get this quantity as the rate constant. So, if you put this as a rate constant k, then you see that the kinetics are given by the parabolic rate constant with a k as a rate constant. Now, to see whether we have the same reasoning for the whether the model is correct or not, that can be only assessed, because in this model the way we have made the assumptions, that we have already made the assumption that the kinetics are controlled by the nitrogen diffusion in ferrite. Ferrite is actually controlling the diffusion of the overall growth of the nitrided layers. That is what is actually the assumption here, because here we are taking actually the only the diffusion of nitrogen, that moment that happens automatically the layer will start to grow, right. So, that is not at all a rate determining step. The rate determining step is the nitrogen flux which is reaching at the end of the nitrided layer, nitrided region, right. So, that is where actually one can do such analysis, and such kind of analysis has clearly shown that is this model works quite satisfactorily for this kind of situations of like iron chromium, iron vanadium and iron titanium. So, in our tutorial we will have actually one set of data where we have the layer growth kinetics data which has been measured for different temperatures, and then we will see actually how one can actually verify whether the model is working or not as it is assumed. So, with this now I am at the end of this lecture. So, and as in the overview lecture I have also remarked on doing nitriding dedicated nitriding treatments for the stainless steels. So, that part we have actually not covered. So, but I will actually explain very briefly why it is very important to do a dedicated treatment of nitriding to harden the stainless steel surfaces. So, the stainless steels are having a significant amount of chromium, that is what gives the stainless character for these steels. Unfortunately, this chromium has a strong affinity to both nitrogen and carbon. So, if you try to do carburizing, there exists a huge thermodynamic driving force for the chromium to precipitate out as chromium carbides or chromium nitrides in case of nitriding. Both of these processes will remove the chromium from the solution and form chromium nitride or carbide precipitates. That way your matrix around the particles will lose its corrosion resistance. So, we will reach the hardness levels, but at the cost of losing the corrosion resistance. So, the only way to harden these stainless steels is to do the nitriding or carburizing treatment in such a way that you will only allow the nitrogen to dissolve into the surface of the samples without forming any carbides or nitrides. So, that can be achieved with doing a low temperature treatments where the diffusivity of substitutional chromium is relatively much smaller as compared to the diffusivity of nitrogen. So, in such kind of a situations, and if we impose a very high chemical potential of nitrogen in the gas atmosphere, that by that we are imposing actually large driving force for diffusion of nitrogen into the sample, then one can actually produce only so called nitrogen dissolved austenite layers on austenitic stainless steel surfaces. So, this is simply the effect of the solid solution hardening by the interstitially dissolved nitrogen. So, that is actually a very dedicated treatment. So, I could not cover that in this lecture series. So, but if somebody interested in that can read these references which I have cited in the previous lectures, the thermochemical surface treatments. It is an edited book by Marcel Somers and Mittermeier. Thank you for your attention.